Okay, guys, this is going to be the introduction to Chapter 9, which will deal with exponential functions to begin with. So this was actually a little warm-up here um, that just kind of shows some of the different functions that we've talked about so far this year. Okay, so I just kind of wanted to touch briefly on these. The first one there, just y equals 2, is just kind of a constant function, it's called. It's just a straight line. The y value is 2 throughout, so horizontal line. And then of course part B there, y equals 2x, that's going to be in the linear family with a slope and a y-intercept. So in this case, remember it'd be like mx plus b. The y-intercept would be 0 and it would have a slope of up to over 1, so it would go through that point and so on. Um, part C, y equals x squared, so that's the quadratic family. We looked at those quite a bit. Um, Gives you a parabola. Part D, y equals x to the 1/2 power. So you can raise x to a power if it's a fractional power. You remember there's a way to write that as a radical where it would just be kind of like x, the square root of x, because the 2 would actually be the index out here, and it would be x to the first power. And when the index out there is 2, it's just a normal old square root of x. And we looked at their graphs. They kind of look like the one over here where we start at the origin and kind of grow slowly. Um, the new ones here, E and F, those are exponential functions, and the thing that stands out about them is that the variable, the x, is in the exponent. Okay, that's why it's called an exponential function. So it's not that it just has an exponent, because even quadratics have an exponent, and so did our x to the 1/2. But the difference is here that the exponent is a variable, okay, or has a variable in it. So we'll see what those look like. But for now, if you were to just go in your calculator real quick and go to y equals and do 2, raise it to the x power with the caret key, it should look something like this, that kind of shape. And we'll see some detail in a second. And likewise, part f there, it's still an exponential function. It just happens to have a different base, and we're going to talk about that. But if the base is 0.5, that graph would actually look kind of the opposite and kind of decrease this way. Okay, so that's kind of what we're going to get into. These are the two new ones here. So if we take a look, the standard form for these things, so you can kind of know that it's exponential. Again, the key is that the variable is an exponent. Um, and they'll generally look like a times b to the x. Okay, and a and b are just going to be numbers. Um, and just a little background on that. Here's what I'm kind of think about. A is going to be known as like an initial value or a starting value. Okay, so you're going to start with some value and you're going to multiply it by b. B technically stands for the base. It's basically another way to think of it is it's the growth factor or the decay factor. If this thing is decreasing, we call it a decay. Okay, and it's basically what you're multiplying by each time. So we'll talk about that. And since the exponent is x, as x gets bigger, remember an exponent means to multiply by that thing over and over and over and over. Okay, so let's take a look at a specific example down here of y equals 3 to the x. Okay, and of course this is something you could throw into a calculator if you wanted to, just to pull up the table. But let's kind of go through some of the details. To do it on the calculator, you just use the caret key, 3 to the x power, and you could pull a table up. But let's kind of see where these numbers come from and get an idea of it. And let's actually start with the when x is 0. So I just made a little table just to see what's going on. so if x were 0, y would equal 3 to the 0 power. And there was a little property, anything to the 0 power actually equals 1. Okay, so the point 0, 1 is going to be on the graph. Okay, and let's go ahead and do the positive values here. If x were 1, it would be y equals 3 to the first power. Okay, 3 to the first power is just 3, so 1, 3 is on the graph here. Okay, and then continuing, again, now if the exponent is 2, 3 to the second power is 9. Okay, so 1, 2, 3, 4. Looks like I need a little bit more room here. So 1, 2, 3, 4, 5, 6, 7. Let's just extend it a little bit. And 2, 9 would be up here. Okay, so it kind of looks like it's growing. Maybe it looks linear or not. Let's take a look. Let's see what happens if we throw in a negative 1. Okay, if we go y equals 3 to the negative first power. Okay, we just got to remember a negative exponent means it goes in the denominator of a fraction. So it's 1 over 3. It's 1/3. Okay, so just kind of estimate negative 1, 1/3. That's, somewhere down here. And as we go farther negative, if the exponent was negative 2, okay, that's going to be 1 over 3 to the second power. That's going to be 1/9. That's even smaller than 1/3, so it's kind of hard to draw these in here, but what ends up happening is they definitely grow as you go to the right, and as you go to the left, as you go more negative out here, the values will get closer to 0. They will approach 0. Okay, so it's never going to like actually hit 0. 0 is kind of like a horizontal asymptote here, if you remember back from the rational chapter. Okay, so that's kind of what the graph looks like. Domain and range, again, just to kind of analyze this stuff a little bit. The domain, again, asks what x values could you use? Okay, or what x values will this graph go through eventually? And it looks like, on both ends here, this thing's going to continue going through the negatives. Okay, it's going to continue going through the positives, and if you think about it, you could plug in anything you want for x. You can raise 3 to any power you want, and you'll get an answer. Okay, so the domain is going to be all real numbers here. Okay, now the range, if you think about that, it's saying which y values or which outputs will you get. Okay, and you can kind of tell from our table, the y values will just keep getting bigger and bigger and bigger. Okay, the y values are just growing here. And you can see on the graph, the y values are going to get bigger and bigger and bigger. So there's no upper bound, there's no maximum. But on the left side here, we kind of said they were getting close to 0. So they'll never actually reach 0, the y values now. Okay, and as you can see on this side, they're getting smaller and smaller. So the range can be any number as long as it's greater than 0. We can't put the equal sign because it will never equal 0, but y could be any number greater than 0. Okay, so that's kind of a basic graph here. Here's another example. Oh, let me go back to that one. I want to point one thing out. I know we said the general form was a times b to the x. Right, we were saying there's this a value. Our graph just kind of had this piece, the one we just did, 3 to the x power. Okay, so a lot of times that a value is just assumed to be 1. Okay, if there's no number sitting out front there, you can think of it as a 1 there. Okay, so let's look at one that actually has an a value, and let's look at one that has a fractional b value. Okay, so here's kind of our y equals 6. Oops, let's do the variables. This y equals a times b to the x. Okay, and we got to remember a couple things. With the order of operations, we got to do the exponent first. I need to do I need to do 1/3 to the power before I multiply by 6. I cannot multiply the 6 times 1/3 first. Okay, it just doesn't follow the order of operations. So let's do this similarly. Let's do the one when x is 0. Let's kind of start here and see where we're at. So if x were 0, y would equal 6 times 1/3 to the 0 power. Okay, and again, 1/3 to the 0 power, anything to the 0 power is just 1, and 6 times 1 is just 6. Okay, so 0, 6, let's kind of just put that in the middle there. Notice I scaled my y's a little differently, and we'll see why in a second here. Okay, what about if we did to the first power? Let's say we want to do an x value of 1. If my equation were y equals 6 times 1/3 to the first power. Okay, well 1/3 to the first power is just 1/3. Okay, and 6 times 1/3 is 2. Okay, so so when x is 1, y is 2, so that's getting smaller. Okay, what if we did an x value of 2? 6 times 1/3 to the second power. Okay, well what's 1/3 to the second power? That's 1/3 times 1/3, that's 1/9. Okay, and 6 times 1/9, 6/9. Okay, if we reduce that just to get a little easier number to work with, that's 2/3. Okay, so 2/3. So again, smaller and smaller. So this one, it looks like as we go to the right, these y values are getting smaller and smaller. Okay, and let's see what happens as we go to the left. What if we did -1 in there? Let's fill in our table for -1. Okay, if we do a -1, 6 times 1/3 to the -1 power. So now again, doing your exponents first. When the exponent's negative, remember it means you can take the reciprocal and make the exponent positive. Okay, negative exponent always means reciprocal. So 6 times 3 over 1 to the first, that's 6 times 3, that's 18. Okay, so when we're at -1, the y value is up at 18. Okay, and let's just finish the last one. If it was -2, if the exponent were -2 now, let's just rewrite this here. 6 times 1/3 to the -2nd power. Oops, let's do that, the fraction. 1/3, okay, to the -2. Okay, 1/3 to the -2nd. Again, it's the reciprocal to the +2nd power. That's 3 to the +2nd power. That's 9. 6 times 9, this is 54. So when we're at -2, we're way up here at 54. So that's why you get this other looking shape that's kind of decreasing. Okay, and the reason that happened, if you think about it, it all depends on what that base is. What are we multiplying by? So in this case, you're taking some number, and as the x values increase, that makes you multiply by 1/3 again and again and again. And you can kind of see that in the pattern in the table. Multiplying by 1/3, that's just like dividing by 3. And look what happens to your numbers here. 54, if you divide that by 3, okay, or times by 1/3, same thing. 18, divide by 3. 6, divide by 3. 2, divide by 3. So that's why you kind of get that. This is called a decay. When this b value is less than 1, if it's a fraction in between 0 and 1, you're going to get that decay in there. Okay. And another way to think about this, notice about where we started. That's always going to be what your a value is. Okay, so you can kind of get that a value plugged in and graphed, and then just ask yourself, all right, since I'm timesing by 1/3 over and over, so I'm going from 6 times by 1/3, I go down to 2. Times by 1/3, I go down to 2/3. Okay, so that's kind of the background. Again, your calculator can help you with some of the calculations on those. Okay, so this we kind of just mentioned, the kind of new vocab, though, growth versus decay. If your general form, again, for all these is y equals sum a times sum b to the x power, we showed one of each. The first one we did, it was 1 times 3 to the x. That one was kind of growing like this. So the rule is you get growth whenever the b value is greater than 1. Okay, and if you think about it, if you take any number and you times it by something bigger than 1, you're going to get a bigger answer. Okay, and the graph will look like that, where as it goes to the right, it increases. The other option is this decay. We saw the graph look like that. This is one we just finished. This is when the b value is between 0 and 1. Okay, so it's going to be less than 1, but it's going to be bigger than 0. And you might ask what happens if b is negative, because that's not listed on one of the options here. When b is a negative number, if you think about what happens when you raise a negative number to a power, if the base is negative, it kind of screws things up and you get this weird looking graph. Like just take, for instance, let's say we took like -2 to the x power or something. So if that b value is negative, okay, as x increases, so let's say this is y equals, and let's just go through a couple real fast and we'll see the pattern here. So if x were 1, -2 to the first would just be -2. But if x were 2, -2 to the second power, -2 times itself is actually a +4. If x were 3, so that would be negative 2 times negative 2 times negative 2. That's going to end up being a negative 8. So what happens is these kind of just alternate from positive to negative, and you get this weird looking graph where it kind of like jumps around like that kind of thing, and it doesn't fit this situation. So we're not really going to worry about that. It's not going to show up. Okay, so let's look at a good example of this. You might have heard um, from time to time they might say, something is growing exponentially, or something's decaying exponentially, and it kind of brings to mind maybe something like it's growing really fast, or something like that. Like you might hear cells grow exponentially, or whatever. So let's kind of talk about what that means. This is a good example about the number of cell phone subscribers. It's probably growing exponentially, and it may have capped out or slowed down since this data was out, but definitely from around 1995 to 2005 was really exploding, and growing pretty quick. So let's see what we got. So we got some data here. In 1995, there was 154,000 cell phones. Okay, by 2005, that number had grown to over 194 million. Okay, so let's think about this. Key here is we're going to use our x value as the year since 1995. So I'm going to kind of act like, just for this situation, that 1995 is like the beginning of time. That's when we have our starting value. So that's going to be like x equals 0, basically. Okay, that's when we're starting. That's our value. So the point on the graph, the year since 1995 would be 0 years since then. And then the y value, the 28,154,000. Okay, so that point is here. That's kind of like our y-intercept. That's our starting value. And then as time goes on, okay, so now we're at some new time. We have a lot more cell phones. So in 2005, that would be 10 years later. Okay, 10 years since 1995. So the x value is 10, the y value is this big number, 194,633,123 zeros. Okay, so we have this growth going on. Okay, and again, this was 10 years later. So we need to come up with an equation to model this. What if we want to predict what's going to happen in the future, or what happened in between, make a prediction. So we want to write an exponential equation, okay, to model the number of cell phones in the US. We're going to let x represent the number of years since 1995. Okay, so if you were new to this, or if this was, a few years ago, and you see 2 points like this, you kind of automatically assume, let's say it's linear, and let's find a slope and do a y-intercept and all that good stuff. Okay, and that would be fine if it was linear. Okay, but this is not. Okay, this is exponential. Okay, we're assuming we're getting some sort of curved growth, and it's going to start growing faster as it goes. It's not a constant increase. It grows faster as you go. Okay, so what we need is to figure out how fast is it growing. What is it multiplying by each year? Is it doubling each year? Is it times 10 every year? Who knows? That's what we got to find out. Okay, so to do these, we got to think about the general form, okay, which is y equals a times b to the x. Okay, and again, remember that I said the a value is kind of like the starting point. Okay, so for our example, this is going to be the a value. That's like when we started keeping track, that's where we were. Okay, so a little trick, the a value should usually be paired up with a 0 as the x value, because it's at time 0. That's when we started. Okay, so we know that. We know a. Now the b is the thing we're trying to find out. Okay, this is the thing we don't know. We want to know. So luckily, when they give you another point, they're giving you an x and a y to plug into the equation. Okay, that's like some later point. So we're going to try and plug everything in and see if we can solve this for b. Okay, so our equation will be the y value, let's move this up a little bit, was that 194 million, 633,000, 194,633, 000. So that's y equals a, okay, the initial amount of cell phones when we started, 2154000. times some b, which we don't know. That's the variable here. And then the x value is 10 from the point they gave us. Okay, so we need to solve this equation for b. Okay, so right now it's some big number equals some big number times b to the 10th power. So we are allowed to divide both sides. Okay, so let's do that. Let's divide by the 28154,000. Let's do that on both sides. Okay. Let's throw that in a calculator carefully because there's a bunch of zeros. 1, 2, 3, 28154,123, and I got 6.913. Let's just stop there. Okay, let's round it to the nearest thousandth there, just to be safe. Don't call that 7. That's a little too far. You know, if you want to go 6.9 or 6.91, but carry it relatively far. Technically, just so you guys know, when you're doing problems, you're not supposed to round until the final step. Okay, but that's, you know, not a huge deal as long as you don't round too short. So we should be safe here. Okay, so 6.913 equals b to the 10th power. Okay, we want b. So if you think about, if we knew what b squared was, we could take a square root. Okay, but we don't. We know what b to the 10th power is. So the trick, the way to get rid of that 10 as an exponent is raise both sides to the 1/10th power. Okay, to the 1/10th power. Okay, and notice what happens. Okay, on the right side here, remember this is a power to a power. Those exponents can get multiplied together. And 10 times 1/10 is 1. So this is just b to the first, or just b. Okay, this left side is going to need to be done on a calculator. Now here's where I would get away from the rounding. Hopefully you have that whole decimal in your calculator. Just hit the caret key and it should say answer, and then raise that answer to, in parentheses, the 1/10th power. Okay, so I'm doing answer to the 1/10th power. And my calculator gave me 1.213. Okay, that is our b value. Okay, so we can write the equation now. Okay, so the equation would be y equals, we knew the a value. Okay, with the initial value was that 281 million, 281,540,000 times, we just found b to the x power. Okay, we found out how much it was growing. Okay, a couple things we found. We actually knew the initial value from the very beginning of the problem. That was given to us. So that we knew from the beginning. We went through and found that. And now x, again, remember, is just going to be the number of years since 1995. So if they want you to make a prediction, okay, like part B, what do you think is going to happen in the year 2015? So if we assume this rate of change or this growth is you know, this equation is still holding, let's estimate the number in 2015. Okay, so we just need to figure out what will we use for x. Okay, I know the equation's y equals 281,540,000 times 1.213 to some power. And remember, the exponent is the years since 1995. Okay, it's kind of asking how many opportunities did it have to grow. Okay, we know it's growing by this amount each year. So since 1995 to 2015, sounds like 20 times, 20 years to grow. Okay, so if we just throw that in the calculator, we can get our answer. Let's do that. Again, I'm going to use the answer. That 1.213 is still in my calculator. And I got, big number here, let's just write this, 1, 3, 4, 5, 5, 2, 8, 3, 3, 3. Okay, so that's how many subscribers we would expect if the growth rate was still going as what they said it was. Okay, let's set up one other quick problem here. This one a little bit smaller, numbers a little bit nicer. So let's say we want to write an exponential function. Goes through 0, 3, and then negative 1, 6. So just to kind of get a little visual here. So we got 0, 3, and negative 1, 6. So we got a point at negative 1, 6 up here. We got a point at 0, 3. Okay, and we know it's exponential, so it's doing something like that. And let's see if we can figure out the equation here. So there's 0, 3. Here's negative 1, 6. Okay, and since it's exponential, again, we know the format a times b to the x. Okay, so we know, again, the starting point, that's going to be our a value. Okay, that was where we are when time is 0, or when x is 0. The other point is an x and a y. Okay, if we plug those in, a was 3, b is the thing we don't know. Okay, we know x is negative 1. Okay, here's the little difference on this one. The exponent is negative. Okay, so sure, we can still divide both sides by 3. Okay, so 6 over 3 is 2. 2 equals b to the negative first power. What is b to the negative first power? Okay, I guess there's a couple ways to do this. We want to know what b to the first power is. Okay, so one way is think about what power could you raise this to. Okay, we're going to put some exponent out here where the product of the exponents, when I do that times that, equals 1. So wouldn't it work if I rose that to the negative first power on both sides? Okay, over here negative 1 times negative 1 is positive 1. So this will be b to the first power. And then 2 to the negative first power, remember it's a reciprocal because the exponent's negative, it's 1/2. Okay, so that should be our b value, and that's all we need to write the equation. The equation would be y equals what we started with, times the b value to the x power. Okay, and that's our equation. Okay, and kind of look at it, see if it makes sense. Take a look, is our starting value, okay, that was our starting value. Okay, as we move on, as we increase x values, the y values are getting cut in half. As we're moving this way, the y values are getting cut in half. As we move to the left, the x values are getting doubled. We went from 3 to 6. The next point at negative 2 would be way up at 12. Okay, so this kind of fits. Okay, so that was what we're looking for in 9.1. For some practice, we're going to look on page 504, numbers 19 through 33 odd. Okay, so you're able to check your answers. I want you to check your answers, make sure you're doing them, getting them correct actually, and make sure we're showing the steps here. This, like pretty much every other unit we've ever done and ever will do, we're going to build on these kind of basic things, so try and keep your steps and everything organized. Okay.